at 2. Good morning, everyone. Good morning, Mr. Guillaume Lorilleux. I'm sorry if I pronounce you wrong. Okay.
Good morning. Good afternoon.
Yeah. Okay. Good morning. Welcome to the 5th webinar series brought by Mgei Economy Indonesia. And today the topic is nickel laterite deposit, part 1, geology and metallurgy. And I am Aditya Rizky Bowo, and I will be your moderator for this season. Thank you for joining this afternoon, and we very honored for Mr. Guillaume, very special speaker today. Okay, please allow me to speaker today, and let me share screen. Oke, masuk ya share screen saya ya. Ya, ya. This is Dr. Guillaume Lorilleux, General Manager of Resource in PT Merdeka Mining Services. He's a seasoned geologist and mining professional over 18 years in international experience, including in the Southeast Asia, Australia, as the current position is the Director of Geology. Now, the education background is equally nationally superior geology as the geology.
May I interfere for 1 second?
Oh yeah,
I'm sorry,
yeah.
Aditya. There are a few mistakes in this slide, actually. So a few major ones. So I'm not Director of Geology for Southeast Asia at Oricha, for example. I'm working currently for Merdeka. So there are a few
Oh yeah, sorry.
things. Yeah. So just for everyone, there are a few typos here. Same for my doctorate, is not from this university, it's a different one. And I've actually more than 18 years of experience, but I'll let you go.
Sorry, sir. Okay, so the profile of experience for now in the PT Merdeka Mining Services as a General Manager Mineral Resource Group. Okay, I think that's all for the introduction. And please, for our distinguished speaker, the time is yours.
Thank you. Hello, everyone. I might probably know a few of you. I will start to share my screen. Bear with me. Share. That should work. All right. Do you see my screen, like presentation, the slide?
Yeah, it's already on screen.
Perfect. So I will start then. So this talk is about geology and metallurgy of nickel laterite. It's really a sharing knowledge session. And what I will present is mainly based on a literature review on New Caledonian deposits and on my experience working on nickel laterite deposits in New Caledonia and Indonesia as well. Beyond sharing insights on nickel laterite deposit geology and classification systems, the purpose of this presentation is to set the scene for the next week's session related to mineral resource estimation of nickel laterite. That I think is very important for resource estimation geologists to have a good understanding of the geology and the genesis of nickel deposits. So That's why I organize this webinar in two parts. And there will be time for questions. If you have really burning questions, you can interrupt me. But if possible, I would prefer to keep the discussion at the end. Okay, so in 1864, a French mining engineer and geologist named Jules Garnier found a green rock along the Dambea River in New Caledonia. And it was a new nickel-rich magnesium hydrosilicate that was later called Garnierite, as you can see on these pictures on the left. This triggered a green gold rush in New Caledonia, and mining began to develop very rapidly after 1873. That was really the onset, actually, of the mining industry related to nickel laterite. The development of nickel laterite deposits is controlled by the interplay between a number of related geological and environmental factors. Internal factors can be described as bedrock lithology and structure, water table variations. External factors include climate, eustasy, and tectonics. The response of the system is the development of erosion and weathering, which in turn influence the structuration of the bedrock. We will first focus on the role of lithology and climate on weathering. So the lateritic profile results from the process of weathering by meteoric water of an ultramafic substrate under a tropical climate. It is a complex process that includes chemical reactions and mechanical processes like compaction. This figure represents a typical weathering profile with smooth variations of major and minor elements and smooth distribution and proportion of mineral phases. The dissolution of the peridotite silicate minerals by acid meteoritic water is associated with the removal of mobile elements, mainly silica and magnesium. As you can see on these curves here, the decreasing concentration upwards of magnesium and silica. The least soluble elements, iron, aluminium, and chromium, are more and more concentrated, going upward by residual enrichment. Very few clay minerals form as a result of the low aluminum content of peridotite. Nickel, cobalt, and manganese have intermediate solubilities and are enriched in saprolite and or in the lower part of limonite. The bedrock main primary phases, the olivine, pyroxenes, and serpentine, are increasingly weathered going upward. Olivine disappear first, followed by serpentine that can persist in the lower part of the limonite. Chromite is resistant to weathering and persists in the entire profile. Secondary neoform phases consist of secondary serpentine and garnierite, mainly in saprolite. Manganese oxides in the transition zone and lower part of limonite, and iron oxide increasing upward and becoming the main mineral phase in limonite. The partial dissolution of peridotite generates a porosity which increases upward in the saprolite as the weathering is more advanced, leading to a decrease in wet bulk density from about 3 grams per cubic centimeter in the peridotite, depending on its characteristics, down to less than 1 gram per cubic centimeter in extreme cases in the upper saprolite. Such a low density ore is called minerai bouchon in French, in New Caledonia, which is called cork ore in English, and can occur when structures are present, preventing the rock from collapsing. This is an example of saprolite ore with quartz garnierite structures at Poro in the eastern part of New Caledonia. And a typical example of saprolite where the density is very, very low. In the limonite, all the silicates being dissolved and the porosity collapse, leading to compaction and an increase of the bulk density upward. The upper ferric layer mainly consists of iron oxide or hydroxides, with a wet bulk density also very high, close to around 3 grams per cubic centimeter. So how can we obtain economic nickel grades by weathering of peridotite? The reported rate of weathering are in the range of 50 to 10 meters per million year. And therefore, a 50-meter thick laterite profile may accumulate in 1 to 5 million years under steady state conditions without erosion, and may represent up to 300 meters of transformed bedrock. So as you can see on the left figure, considering that 1 meter of limonite results from the weathering of 6 meters of peridotite, and considering a dry density of 2.7 grams per cubic centimeter in bedrock and 1.1 gram per cubic centimeter in limonite, 0.3% nickel in bedrock would be converted into 4.4% nickel in limonite. However, as we know, nickel grades in limonite are generally less than 2% nickel, suggesting that some nickel has been leached. In the saprolite, considering a mass loss of 70%, the theoretically computed residual enrichment alone would result in 1% nickel, considering the same density and grade hypothesis as before. This shows that residual enrichment is not sufficient to explain the higher mean nickel grades which can be found in saprolite. Other factors are therefore necessary to explain the observed nickel grades. Nickel in limonite is probably leached by downward circulation of acid meteoric waters, reducing the limonite grades to less than 2% nickel, and increasing the nickel grades in saprolite by precipitation of nickel-rich hydrous magnesium silicate, responsible for an absolute enrichment in saprolite. This is suggested and shown by mass balance calculations, as shown on this middle figure here, that show that nickel is lost in limonite and gains in saprolite. This leaching would be obviously favored by tectonic activity and structures controlling the underground field circulation. Many mineral phases incorporate nickel and cobalt. Nickel may substitute for iron, magnesium, aluminium, or manganese. In the fresh peridotite, so this slide represents basically a profile with bedrock, saprolite, and laterite going upward. So in the fresh peridotite, nickel is mainly contained in olivine and serpentine. During weathering, nickel is released from olivine and fixed on primary serpentine by physical adsorption and hydrolysis. Nickel is also leached from olivine and primary serpentine and fixed on hydrous magnesium phyllosilicates, and subordinately by oxides such as goethite in the saprock. This trend is reversed in earthy saprolite, where goethite is the main carrier, with some residual phyllosilicates still detected. These hydrous magnesium silicates consist of neoformed garnierite and of secondary nickel-enriched early serpentine. The weathered early serpentine greatly contributes to the nickel grade, and in some places is the main nickel-bearing phase. The degree of serpentinization, pardon me, the degree of serpentinization of the parent rock is therefore an important factor in mineralization and is as important than the degree of weathering. Garnierite is a mixture of 3 minerals, serpentinite, talc, and smectite. which all vary in composition between magnesium and nickeliferous end members. Garnierite generally forms when early serpentine and iron hydroxide are saturated in nickel and precipitates as coatings, boxworks, and vein infills following shears, joints, and grain boundaries. At the base of the limonite, in what is called a transition zone, manganese oxides may incorporate an important part of the nickel. This zone contains dark manganese and cobalt-rich concretions that include the phyllomanganoate family hasbolane, lithophorite, and birnessite. In limonite, nickel is mainly hosted by iron hydroxide, predominantly goethite. The nickel in goethite may account for about 75% of the total nickel in limonite, whereas hasbolane and lithophorite may account for about 25%. The decrease in bulk nickel content in limonite towards surface might be explained by aging of goethite in situ through successive dissolution and precipitation cycle, as shown here, during weathering in the fluctuation zone of the water table, and also by dissolution of manganese oxides. Adsorption appears to be transitional since after its release from silicates, the adsorbed nickel further passes to the lattice of the goethite or precipitates with it. The process is fully controlled by the pH front and its shape. Nickel is more strongly adsorbed at high pH values. Adsorption of nickel is significant in a narrow range of pH due to the competition of magnesium and nickel for sorption sites of goethite surfaces. The minerals having the highest content in nickel are in saprolite and lower part of limonite, as we have already seen. Yes? Can you hear me well, just as a check?
Yeah, it's fine.
Okay, I heard a voice.
Yeah.
All right, thank you.
Yeah, good.
Now we describe the lithological controls. The nature of ultramafic lithologies may influence the type of weathering minerals and subsequently nickel enrichments, as well as the intensity of weathering. For example, aluminium-rich lithologies will favor the development of clays. In terms of mineralogy, olivine will be weathered before other peridotite minerals, as we have seen before, as shown on this diagram. So on this olivine orthopyroxene, clinopyroxene diagram, you can see that the weathering would be faster for the dunites, which are rich in olivine. On this picture, you can see dunitic beds, which are weathered faster than harzburgite. So that is a good illustration for this diagram. The different mineralogical compositions and competency of dunite and harzburgite have an influence on the weathering, fracturing, and mineralization. However, in some cases, harzburgite appears to be more weathered than dunite, possibly due to the more compact texture of dunites. Therefore, the intensity of weathering reflects both the nature of minerals and the rock textures, affecting the micropermeability. Serpentinization is also an important factor, and the degree of serpentinization of the protolith appears sometimes correlated with the nickel enrichments. In New Caledonia, the serpentinization intensity decreases from the sole of the peridotite nappe upwards. This serpentinization is related to four-arc serpentinization of the mantle wedge by dehydration of altered oceanic crust during subduction, as well as serpentine salt formation by late meteoric fluid percolation at shallow depths during abduction. It is later than hydrothermal oceanic serpentinization. In New Caledonia, the soul of the peridotite nappe consists of a serpentinite, milonite, sometimes reaching several hundreds of meters in thickness. This photograph is an illustration of the serpentinite soil at Konyambo deposit in New Caledonia. The serpentinization degree and weathering both impact the texture and structure of the regolith. The differences are exacerbated in saprolite, where the weathering is not intense enough to erase all textures. So serpentinization, peridotite appears as massive blocks, and mineralization is focused in a fracture network within earthy material or garnierite veins. As the serpentinization degree increases, boulders display onion peel textures, and a fresh peridotite core is surrounded by hard and earthy saprolite, which are both generally mineralized. With higher levels of serpentinization, the peridotite boulders show a progressive transition from the core to the edge with a more diffusive mineralization. And in the case of strong serpentinization, the peridotite is deeply weathered with abundant earthy phase and rare boulders. Okay, now I will talk a little bit about karsts. This is actually obviously related to the weathering. Karst landforms are commonly described in nickel laterite deposits. The processes are similar as for karst developed in limestones, but in a limestone environment, the rock dissolution is almost total, whereas in the case of laterite, the dissolution is partial and leaves a residual material corresponding to the saprolite. So these are illustrations of dolines, which is one of the most common exokarst fissure in new nickel laterite, generally developed at fault intersections. You can see on these pictures a huge doline at Goro in the south of New Caledonia with loss at the bottom of the doline. Another example of doline here, and this is in Thio deposit, one of the deposits at Thio on the east coast, with verticalization of the regolith profile near a doline. Jenna and Sevin modeled doline formation and geometry as shown in these figures on the left. And one noticeable feature is deepening and disruption of the regolith layers. Endokarst features like subvertical dissolution pipes, locally containing collapsed breccias, developed preferentially along pre-existing serpentine faults and have been described in several deposits in New Caledonia. Local collapse of the pipes by gravity collapse formed breccias cemented by quartz as well as nickel-rich talc-like garnierite on the rim of clasts, as you can see here on this drawing, related to evaporation during drier climatic episodes. We will now focus on the influence of other external factors, notably tectonic activity and associated variations of the water table. The influence of the tectonic controlling factor is reflected in the geomorphology. There are three main deposit types based on geomorphology commonly described. The basin type, as with an example here in Goro in the south of New Caledonia, the plateau type, subdivided into continuous plateau and dissected plateau, with two other examples, again from New Caledonia, and the slope type. The different geological types are end members, depending on the competition between the efficiency of chemical weathering and efficiency of physical erosion related to uplift. The basin type corresponds to the predominance of weathering over uplift, which allows the preservation of a thick sequence of limonite, saprolite being poorly developed due to the low drainage. The plateau and slope types correspond to the predominance of uplift over weathering with the development of high-grade silicate mineralization in saprolite. The plateau deposits are topographically inverted former basins. Uplift increases from continuous plateau to the slope deposits. As the level of uplift increases, erosion also increases, leading to truncated laterite sequences and thinner limonite relative to saprolite. The importance of slope ruptures increases in dissected plateau and slope types and is associated with the development of deposits on the flanks of the massif. This is a different illustration of the geomorphological deposit types from Sevin and can be simplified into the same categorization: basin, plateau, and slope. Basin deposits can be very large and characterized by a typical flat morphology with low relief surrounded by crest lines. Plateau deposits are generally large deposits located in plateaus or mountainous, elevated areas. Continuous plateaus are less impacted by erosion than dissected plateaus. In continuous plateaus, the topmost resistance ferricrete is continuous, and it armors and protects the softer underlying horizons from erosion. In these deposits, oxide and hydrous magnum silicate ore coexists. In dissected plateaus, most of the upper part of the weathering profile has been eroded. In this case, hydrous magnesium silicate ore is predominant in these deposits. Slope deposits are found in the highly dissected mountainous domains, spread out into numerous small deposits on ridges and flanks. Landslide morphologies are common in this specific setting and on most plateau edges. The deposits in these gravitational structures are primarily controlled by extensional faulting and gravitational collapse. They may be limited at the base by a concave upward fault underlining a heavily fractured and highly weathered lens. This is a more detailed illustration of basin-type deposits, showing typical lateritic profiles and cross-sections. They generally present a continuous ferricrete cover studded with sinkholes, lakes, and wetlands, and are more or less dissected by a few rivers. Some of these deposits are concealed beneath terrestrial sediments or drowned below sea level. Their geological controls are loose. They correspond to large weathering cells where the internal drainage is weak, the water table is high, and leaching and precipitation are limited, and nickel enrichment is mainly residual. They are characterized by a thick yellow limonite layer and poorly developed saprolite related to poor drainage. The main nickel ore is located in limonite. The A2 subtype in Sevin classification here on the right is characterized by the existence of fluvio-lacustrine sediments, including transported reworked laterite. Plateau deposits are located in elevated areas where the internal drainage is free. The water table is low, and leaching and precipitation are optimal. Plateau deposits can be truncated with less ferricrete and limonite due to erosion in lower altitude on mountain sides. They are characterized by a well-developed saprolitic horizon due to high drainage. The C-type in Sevin's classification on the right here is characterized by the abundance of smectite and an aluminum-rich bedrock, for example, due to the presence of lerzolite, feldspath-rich intrusive, or gabbro-cumulate and wehrlite. Instead of the classical transition horizon, a gley horizon is present in this category, characterized by the presence of sulfurs, possibly related to the existence of dolines or former dolines underlying an acid superior horizon characterized by high aluminum content and also the presence of non-tronite. This slide summarizes the different morphological style of deposits. So it's a bit repetitive here, but we have again the basin style, the plateau style, and a breakdown of the slope style with subvariations with round ridge and angular ridge in addition of the flat area. Mineralized coccate structures have been described in New Caledonia with mineralized silicates in thin layers cementing joints. Their chemical and mineralogical concentric zoning has been interpreted as resulting from nickel remobilization related to active dissolution precipitation processes of nickel-rich veins. These processes would be caused by evapoprecipitation processes related to alternate periods of hydration and drying induced by water table movements. And similar features have been described also in the unclasts of the collapse breccias of endokarst features. We now focus on the influence of structural controls in relation with tectonic activity. So it's closely related to the previous part, but going in more details on the actual structural controls. The inherited serpentine-rich fracture network controls water infiltration, and therefore the incision of the weathering surface and the deepening of the weathering profile. The plateau deposits are generally controlled by the intersection of two or more orders of structures, resulting in complex patterns such as horst and graben structures, high-angle cross-cutting furrows, and ridged or egg box structures. This is an example here of dihedral trap formed by these conjugate structures. Three main types of structures have been described by Sevin. Order 1 structures are the main structures controlling weathering and the formation of traps for nickel ore, as well as the incision of hydrographic network and the geomorphology of massifs hosting the nickel deposits. So this is these major structures here, and this is an example here of a major faults with some garnierite and dewelite precipitation. This order 1 structure controls water flow enriched in leach nickel, which precipitates mainly in order 2 structures, which are more frequent and less open, and which tend to slow down free circulation and contribute to nickel precipitation. Order 2 structures correspond to the matrix of the trap and are the most mineralized structures. Well, this is an example, obviously, of garnierite-rich veins, which constitute, in that case, the matrix of the trap. The different types of traps for nickel mineralization are dihedron furrows, curved structures, like this one here, and dolines, intersection of structures. When uplift is significant, the subsequent steep slopes, together with circulating meteoric waters with serpentine field fractures, may lead to slope failure. The collapse of plateau edges provoked plateau decompression and hence multidirectional extension. Gravity-driven faulting caused preferential opening of joints within the hanging wall of faults. So this is an example here on this diagram, which favored weathering and eventually resulted in an increase of nickel content in the saprop. So it's kind of a feedback loop here between the structural controls and the weathering. Some of these serpentine field faults have listric shapes and behaved like drains in their vertical part and acted as barrier in their lower part, horizontal part, therefore enhancing the trapping of nickel in the hanging wall of these faults. Such gravity detachment faults can put in contact a double thickness of laterite, as shown on this diagram figure at the top here, and therefore can be an excellent exploration target. Even though these deposits are generally, as I already said, they have small sizes, but the grade can be really high. This slope collapse may be assisted by hydraulic fracturing and crack seal veining, that has been described here on this paper, related to meteoric fluid overpressure in the hanging wall of the fault. This is a synthetic 3D drawing summarizing the structural setting of plateau and slope deposits, with all the one structures represented here, controlling the deepening of the weathering of the geometry of the nickel traps, and all the two structures developed within the weathered volumes, so inside here, for example, controlling nickel enrichments. And gravity faults, for example here, associated with slope deposits and responsible for further nickel enrichments, as we seen in the previous slide. Nickel enrichments tend to increase from basin to plateau and slope deposits in relation with the development of thick saprolite profiles, the effect of erosion after uplift, and gravity-driven processes generating structural and topographical traps. More specifically, in slope deposits, channeling, containment, trapping of the metal-bearing solutions, and feedback between fracturing and weathering is responsible for producing high-grade concentration. The tectonic activity may be responsible for simultaneous formation of nickel-rich silicate veins, a rapid process related to hydraulic fracturing, crack and seal, and the redistribution of nickel downward by weathering as alteration is enhanced and favorized in fracture zones where permeability is higher. And this would explain the actual nickel enrichments described in one of the first slides with this downward leaching of nickel. Additionally, early nickel enrichments in peridotite prior to weathering, so this is very specific, in relation with tectonic activity and hydrothermal field circulation, have been described in New Caledonia. More specifically, the formation of garnierite field fractures and veins and hydraulic breccias in the bedrock have been interpreted by Catlino and et al. As being related to the mixing of ascending low-temperature hydrothermal fluids and descending meteoric fluids. And I know this is a little bit controversial and has been discussed by different authors, but this is something that actually could be merged into a more general model where ascending fluids could actually represent the emergence of descending fluids warmed up basically in a local area by convection. This figure shows the relationships between the development and evolution of karst systems at the top and the geomorphological types of nickel laterite. The onset of weathering is controlled by faults and dolines develop at fault intersection. Closed basins then developed around these intersections and along the structures. The basin type corresponds to the alteration cells surrounded by rocky ridges, I've seen here and I've already seen in previous slides. This basin type is illustrated by this morphological section at Goro. So this is a typical karstic landscape with dolines and underground channels, and this corresponds to the initial morphology of all the peridotite before uplift. With more uplift, basins becomes plateaus by topographic inversion. As uplift increases, the karst topography is dismantled due to erosion by rivers, the laterite becomes dissected, and slope systems develop in relation with gravity-driven faults. The river incision resulted in the stepping of a series of lateritic paleo landforms, as you can see on this picture here. and the development of a pseudo-karst system with subvertical dissolution pipes, as described at Cognambo, as modeled conceptually here. So this is a concept of the development of the Cognambo system by Catlino. Another author, Kennel, 2017, shows that areas richest in nickel are under thin or no laterite or limonite cover at Cognambo. I should say limonite, I'm sorry, this is coming from the French, actually. Based on the nickel mass balance calculations, two complementary processes are invoked. The first consists of the successive lateral transport of reworked laterite material. So it's a mechanical transport, including nickel-bearing material from topographic high to downslope areas. Leaching of this reworked material could increase nickel grades in the underlying saprolite zone. The second process consists of lateral infiltration of groundwater rich in dissolved nickel from high topographic areas to downslope areas. These processes, combined with the preferential development of saprolite in uplifted areas, may be responsible for higher grade of slope deposits. So it's a complementary process. Using reactive geochemical transport modeling, Miyake in 2017 was able to model lateral nickel remobilization and deposition and explain local nickel enrichments in topographically low areas and precipitation of garnierite in fractures. He showed the importance of the downward progression of the pH front governing nickel enrichments as shown on this diagram. So on the left part here, this is some of the parameters and variables that were used for the simulation. And on the right, there are some of the results. And the top diagram shows the propagation of the pH front. So with time, we can see the pH front moving downwards. And nickel in solution also increasing downslope with time. And also the nickel content increasing in the saprolite in the topographically low areas with time, as well as the upper part of the bedrock here. And the last one here, it represents the actual dissolution of olivine. So in the context of plateau slope deposits, the simulation suggests that the most nickel-rich zones in saprolite form usually where limonite is seen or absent, while the areas with lowest nickel are located in topographic highs under the thickest limonitic cover. Therefore, understanding topography, slopes, shapes of bedrock contacts, and localization of preferred fluid flow paths is critical. Now we'll describe the different ore types. So three main nickel laterite ore types are commonly described based on mineralogy. And this is a worldwide classification. Oxide ore on the left, silicate ore in the middle, and clay ore on the right. Oxide ore is characterized by residual nickel enrichments associated with goethite in limonite in low elevation areas with poor drainage and weak structural controls. Manganese oxides can also be enriched in nickel and cobalt at the base of limonite, and a few nickel-rich silicates can remain in the lower part of the limonite. The average grade generally varies between 1 to 1.6% nickel, depending on the cutoff grade. The silicate ore is characterized by nickel-rich hydrous magnesium silicates in saprolite and generally presents high average grades varying between 1.6 to 2.5 nickel, again, depending on the cutoff grade. This ore type is generally associated with good drainage, medium to high elevation, and strong structural controls. The last one, the clay ore, is characterized by nickel-rich smectites, like nontronite, located in the upper part of the saprolite, with an average grade generally between 1 and 1.5% nickel, depending on the cutoff grade again. This type is generally located in low to medium elevation areas with poor drainage, weak structural controls, and high aluminum content of the ultramafic bedrock. So now I will make a link between this classification, this ore type classification, and the geomorphological classification. So this slide shows a simplified model of nickel laterite formation with original ultramafic bedrock, the phase of abduction, a phase of fracturing can be inherited or related to later tectonic activity, circulation in fractures of acidic meteoric fluids, and the subsequent formation of the weathering profile with significant volume loss. In the absence of uplift, oxide and clay ore types develop within basin-type deposits. In the case of uplift, silicate ore developed in plateau and slope deposits. The different ore types, notably silicate and oxide, often coexist in the same deposit, but the predominance of one type over another appears to be linked with the geomorphology of the deposit. So already reaching the conclusion. So nickel laterite is characterized by, is due to lateritic, is the formation of lateritic weathering and associated nickel enrichments, is controlled by the interplay of various factors, as we have seen, including bedrock lithology and structuration, climate, tectonic, water table variations. The relative influence of these factors may lead to different styles of deposits and ore with different morphologies, geometries, size, mineralogy, grade, and different geological and geochemical continuities. All these nickel laterite deposits also have display highly variable grades and density, especially in the vertical direction. And we've seen also the coexistence of two phases in the saprolite. So all these characteristics have implications for how we can estimate the mineral resource of these deposits. And this will be the topic of the next week presentation and discussion. Thank you for your attention. And now I think we have a lot of time for questions.
Okay. Thank you very much. Thank you very much, Dr. Guillaume, for the insightful presentation. Now we will move to the Q&A. Please, if anyone want to ask to Mr. Guillaume, can raise your hand or chat in box. If I may, yeah, it's because I'm moderator. I want to ask two questions, Dr. Guillaume. First, what are the key differences between the laterite types in the Indonesia and New Caledonia? And second, how do we define the transitional zone in the laterite profile?
Thank you. Regarding your first question, and again, my experience of Indonesian nickel laterite deposits is limited, so maybe other people will be happy to contribute, probably. But from what I know, New Caledonia is really characterized by the predominance of plateau and slope type deposits. Basin type deposits are found only in the south of New Caledonia. So from what I know, in Indonesia, the basin style is a bit more widespread, but you can also find plateau style, and I'm not too sure about the slope style. Possibly, I'm pretty sure it exists on the periphery of some of those deposits, but again, my knowledge of the, Indonesian deposits is quite limited, so I'll be very happy actually to hear from if people have some experience of these different styles of deposits. Regarding the transition zone, So there are different ways. I mean, most often it's quite difficult to pick the transition zone visually because it's very progressive between saprolite and limonite. So geochemistry is very often used as with some threshold to define the transition. But in terms of outcrops, it's possible to pick the transition, especially if you have some features related to the collapse in the limonite that can help to define the areas where the actual disruption of the texture of the saprolite starts. But it's not always easy, definitely.
Okay, okay. Okay, thank you very much for the question. Oh yeah, we jump to the next question, yeah, from Andrew Gabata. Based on the chart presented, does saprolite appear to be less dense than limonite?
Yes. Yes, so this, yeah, actually, the density, it's again in this transition zone. The density is the lowest, so bulk density. But as soon as we start to compact in the limonite, compaction starts. So we start to progressively increase the density. But in the yellow limonite, usually, if we go upward from the transition zone to the top of the profile, in the yellow limonite, the evolution of density is very there is not much variations usually in density limonite. So sometimes in estimation we can assume the density is constant. It's not always the case, but it's not this assumption is probably acceptable. But in the top of the saprolite, obviously the porosity is at its maximum. And as I explained, like especially if you have sometimes serpentine structures or different types of structures can still help to hold the porosity in place and maintain this high porosity. So it's quite amazing. I've actually never seen it myself, but it has been described in New Caledonia. There is a specific type of ore which can actually float. It's quite amazing, but just because the porosity has been preserved by structures. So I don't know if it answers the question.
So how the answer, Mr. Enrique Better? You'd like to ask something else or someone?
So next week there will be a bit of a few. I will go back a little bit on some of this concept, obviously, because I will need to talk about it as a base to discuss what methodologies we can use for resource estimation. So we can still have discussions next week if needed, but on this anyway. For those who can make it, of course. I'm aware not everyone can be available.
Yeah, if everyone, if you would like to ask, just raise your hand and open mic, please.
So I just hope everything was clear. But yeah, if you have any doubt or anything, don't hesitate. Any question or anything you would like to clarify.
Halo Pak Bill,
Yeah,
this is Habib from Tujuh Bukit Pak.
okay.
I want
Hello.
to ask nickel because I'm never working in the nickel deposit. So what is the difference between what I call hydrothermal alteration and the alteration in the laterite? That's the first question. The second one is what is the implication of the alteration in the resource estimation from your experience? Thank you, Pak Bill.
Okay, so I can come back maybe to the slides. Yeah. Regarding your first question, I think that could be a good slide for that because this is from an author who actually did some simulation of reactive geochemical transport modeling. So to reproduce the actual conditions of weathering. So you can see here the type of conditions in terms of pH and temperature. So obviously, temperature are low in these systems. So it's not high temperature. I mean, hydrothermal fluids very often will be described with higher temperatures. Even though what I was saying also, there is an author, Catlino and et al. Actually interpreted some low temperature hydrothermal fluid activity that could explain, so going hydrothermal fluids moving upward within structures in the bedrock and mixing with meteoric fluids, descending meteoric fluids, and this fluid mixing could also be responsible for precipitation of nickel silicate. So I would say the difference, it's really more about the characteristics of the fluid. So you can actually have still low temperature hydrothermal fluids, depending on the type of interpretation you choose. Obviously, I think this presentation also shows that there is still a lot of research happening and going on to understand what's happening in these processes. I mean, most of these papers are fairly recent, not very recent, but not very old. And I know there is still more research happening to understand and try to better model the formation of nickel. Sorry, could you please repeat the second question because I missed it.
The second question is there any significant implication from the alteration to the resource estimation?
Implication, is that your question?
Yes, right.
Okay. Definitely, yes. So, and this will be discussed next week. So there is this lateritic profile, obviously. I will go back to the first slides. So here you can see actually a layering with a bedrock, which is a protolith, which is intact or almost intact. And this we separate the saprolite zone from the limonite zone. So there are different stages of the actual alteration, weathering. And in the estimation, it's important to not mix these layers because we know that the continuity, the geochemical continuity and geological continuity is different. And mixing them is not a good idea, probably, to define good resource domains. So as we know, when we go towards, talking about estimation, we will look for stationarity of our variables within estimation domains. So we need to take into account this gradation of the alteration profile. So yeah, so there will be this layering aspect, but we will see also next week that it can be a bit more complex. It's not only a simple layering, sometimes it can be a bit more complex. But I cannot say too much now because otherwise I will spoil. If you're interested, I can send you some, just send me an email. I can send you a couple of papers that there are good synthetic papers. This one from Morizot is really a good one. I really recommend it. It's in English as well, because some of these publications I use are in French. So you may have difficulties to find it in English or even in Bahasa Indonesia, obviously. But this one is a really good one, a very good synthetic publication. I strongly recommend.
Okay, thank you, Pak Bill. Very clear explanation.
Thank you, Mr. Geoscience. Okay.
What
I have
question?
one question from Ahmad Bashar. Please, if you want to ask, open the mic.
Yeah, thank you, Mas Aditya. Pak Gil, this is very interesting topic for nickel. This new also for me because before that I'm involving on the gold project. However, because this is interesting, you said that there is two type of mineralization, which is controlled by basin and or the other one is controlled by structure. Is there any possibility in the one place of the overprint of the type of mineralization between the basin and cut by the structure or vice versa? Maybe is there any possibility of those deposit maybe? Thank you, Pak Gil.
Thank you for your question. Yes. So in general, from the basin style would generally be described as the first stage of evolution before any uplift, if there is an uplift phase. So your question would be like, if there is already a mineralization related to a basin style deposit, I would say yes, it can be overprinted because if you have some tectonic activity that will generate some further structuration and change the morphology and the topography, as I described in some of the slides, you will remobilize obviously the nickel, and you will have some overprints. And another one is that, and this is not related to basin style, but some authors describe some very early pre-weathering garnierite enrichments in the bedrock. And this also obviously would be overprinted or remobilized during weathering. Yes, this definitely happened. And one of the key points of this talk today for me is many people who don't really know nickel laterite in the details have an image of a very simple system with just layers of weathering and enrichment. But in the details, we can see that it can be a lot more complex and also very interesting in terms of geology. And I don't think nickel laterite is necessarily boring. I think it can be really interesting, and depending on where you are, yeah, you can really have some interesting challenge to understand the geology and how the nickel was formed.
Yeah, thank you, Pak Gil. And the second question, maybe if there is time, if there is a possibility of overprint, where is the more high grader or where is the more enriched grade between the basin and the structure, or if it is located on the contact of between the structure and the basin, maybe?
Yes. So yes, definitely the plateau. I think there might be a good slide to illustrate this one. The plateau styles are definitely higher grades, and trying to find. Okay, there are different things. So yeah, so basically what can happen is when you have a first stage of mineralization, which is maybe more diffusive within the weathering profile, if you start to develop some more tectonic activity and development of more faulting and uplifts and system like that, you will be able to, as it has been described, we observe more garnierite veins and structures and text as shown on this diagram in this type of deposit than in basin deposits. And maybe that's why also New Caledonia is maybe famous for its garnierite, maybe why it was found the first time there, because there's so much of it actually. I've seen some deposits with sometimes, I mean, it's not very common, but I've seen massive garnierite breccias, very thick in some deposits, which is very impressive, which I'm not sure we can find this everywhere in basin environment. So yeah, the grades are definitely higher because as the system evolves towards plateau and slope, we tend to enrich the nickel, and this is, yeah, as I described previously, by different processes. And the richest nickel deposits are just generally the slope deposits. They are smaller, but they can have higher grade because of several processes that I described previously.
Yeah, thank you, Pak Gil, for the explanation.
Thank you, Mas Bashar. Is there anyone to ask question?
Hello.
Roger, please.
Hello, good afternoon. Thank you, Pabil, for great explanation about laterite. And from this slide, I just interested that, can you explain what is the difference between Indonesian type of laterite and then with this? Because seem that New Caledonia maybe is too perfect for the enrichment, right? And then in Indonesia, this is different. Maybe you can explain to the people that maybe want to know about the Indonesian laterite as well. And then from this, is it in your place before that you also doing the mapping of the anticorite or tremolite, actinolite or something like that, also to know the map of the structure and then the distribution of the anticorite and tremolite, maybe something like that. Thank you for your time and all things. Thank you. Bye.
Thank you, Rosalind, for the question. The first one is a bit difficult for me, as I was explaining, because I consider I don't know too much. I don't know a lot about Indonesian laterite. I read a few papers and I worked on actually one deposit. But from my knowledge, I've actually observed the existence of very typical basin-style deposits. I can really say that. And I've also observed the occurrence of more plateau style with a very clear link with the topography. So that's why I tend to generalize, and but again, it's open to discussion, and that's one of the purpose of this webinar actually, is really to, as I have a stronger background in New Caledonia, to share this knowledge I have, and also based on this literature review to discuss this with Indonesian geologists who have maybe a different experience. But from my experience, it's applicable, and maybe not in all the types of interpretations, but most of the phenomena, I think, I don't see why it would not happen the same way in Indonesia. And from what I've seen it's more rather because obviously the geological context is a little bit different in Indonesia. So from what I know, there is maybe less predominance of plateau and slope deposits, but they still, at least the plateau still exist. And I suspect the slope there is no reason why it would not exist, but I would be curious to see an example actually. Yeah. And for the other one, yes, obviously many structures, so that's true. I did not describe this here, but as ultramafic minerals are weathered, some fibrous minerals like antigorite, tremolite, chrysotile can form. And this also is obviously a marker of the type of minerals that was altered and a marker of structures, which sometimes is very obvious, yes. So when you are in a mine, sometimes you can see very well these fibrous minerals, sometimes because they are just strikingly white in the more red background. So they can be good tools, yes, to do mapping, structural mapping. Yes, I don't know if this answers your question.
I just want to know the existing of antigorite, tremolite, and others, like to be of hazardous disease or something like that. That you do the mapping or not? Just curiosity. But that before the mining section area.
Yes. Of course. So there is this health and safety concern here, obviously, with fibrous minerals. There is a very strong regulation in New Caledonia about this. And obviously, yes, this is systematically mapped and characterized by geologists during the logging, and it's also when there is a certain level of abundance of some of these minerals. So it depends, of course, of like chrysotile, I think will be one of the worst. And then it depends on the degree of weathering of these minerals. Like weathered antigorite is probably not good as well. So once these minerals are described and their level of weathering, of alteration, and then there is a matrix describing the risk based on both their abundance, type of minerals, and degree of weathering. And with that, there is kind of a classification of areas. And if it's a high risk in terms of fibrous minerals, there is usually a specific way to deal with these samples. And it's quite constraining. Usually, like at the lab, these samples will be treated in a separate batches, maybe, or there will be also, of course, specific PPE for all the people handling this material. And in mine site, very often there are signs and a lot of people make sure that there is a lot of water to avoid dust generation. I think it's one of the key points is really to avoid the dust generation for this, to prevent the risk of inhaling the fibrous minerals. Yeah, I actually don't really know what is the regulation in Indonesia about this, but in my experience, it's very strong in New Caledonia. People are really careful with fibrous minerals. If that answers your question.
Yes, thank you so much. So I just want to have my experience as well that before we have mining section and then I just want to encourage the young generation that if you involved with the exploration of the laterite beside of the mapping, and then also just want to add more from you that you have a great explanation, but I just want to keep remind for all the young generation that we have to do the research for this also, that before the mining section. So as a geologist, we still have a plenty of job beside of the of the drilling section 1 and mapping. Maybe just like that. Just want to inform as well. Thank you so much, Pabil, for your explanation.
Thank you very much.
Thank you for your question. Oh, we still have one question from Mbak Ufi, please. If bisa disappear. Yeah, please, Mbak.
Thank you, Aditya. Hi, Guillaume. How are you?
Hi, Ufi. I'm good. Thank you.
Want to add something, just like you say before, like encourage to explain for you or to add some information with your explanation based on your background before in New Caledonia. Yes, we have the plateau and the basin things in Indonesia. Well, previously, like in my experience, actually, I found it. It's not as big as New Caledonia. You have really big plateau and also basin things. Especially like Tio is a really complex geological with Nepu as well for the Garnerite. But yes, we have it in a small scale. Maybe the age is different because the basement rock in New Caledonia is more older than Indonesia type of nickels, but we have, and we also have like the 3 types of the ore type, like the oxide, the silicate, and the clay as well. Not big, especially for the clay, but it's enough area to if you plan to have like HPAL processing later on, it will be some trouble for that. And for the silicate as well, we have also the sloop, some part, and yes, it's typical of sloop is some part is Garnerite, you can find it, and plateau as well. But a bit tricky when you have infrastructure for mining later on, probably, especially if you have a class want to constrain that in 30 degrees slope later on for the safety of the mining when you want to build the road or some things like that. So you will end up like left some of amount of deposit or ore underneath, something like that. I just want to add that. Thank you.
Thank you, Buffy. Yes, it was good to hear that you have the similar examples. And yes, and also that's true. I did not mention about the mining side of things, but you're right that the mining ratio will tend to increase from basin to slope, and sometimes slope deposits can get quite tricky to mine. And actually, it's quite spectacular in New Caledonia, some of these areas where you have to drive in the narrow, sinuous roads in the mountains for a couple of hours before reaching these small deposits perched somewhere in the mountains, in the clouds, and it's still economic, or I should not say that, depending of nickel price, I guess now maybe not more economic, but it was still worth to mine these deposits thanks to the high grade.
Thank you, Mbak Ufi, for the additional maybe is there any question or the last one? I will count to 3. If there is no, I will close this webinar today. 1, 2, 3. Okay. Now we have reached the end of today's webinar. Thank you very much, Dr. Guillaume, on behalf of Mgei, me, Aditya Rizky, and thank you for all the participants today. We still have, don't forget, we still have the second of webinar at end of July at 3 p.m. SM with this Zoom meeting. And thank you. And please stay tuned for the next part of the webinar. Thank you once again, and goodbye. Thank you. Have a great day.
Thank you, everyone. Thank you
Oh,
all.
I'm sorry. We have please we take a picture first. Yeah.
Oh, okay.
Yeah. Everyone can open the mic, open the camera.
All right.
Sure. Okay. I will screenshot for the first page. Sorry. One. And the second page. 2. Well, we have a lot of participants, 150. And 3. 4. Wait. 5. Okay. Okay. Thank you, everyone.
Terima kasih, everyone. Okay. And talk to
terima
you
Thank you.
next
Yeah.
week.
Okay, thank
See you
you.
next.
Thank you, Mr. Guillaume.
Thank you.
Thank you, Mr. Guillaume. See you.
Thank you so much, everyone. See
See you
you
next
next
week.
week.
Yes,
See you
yes.
next
Thank
week.
you, Guillaume.
Thank you. Bye-bye.
Bye-bye.
Bye.
Bye bye.
Thank you.